It reads, an electrical conductor has a resistance of 5.6 kilo ohms. A potential difference, PD of 9 volts, is applied across its end. How many electrons pass a point in the conductor in 1 minute? And so if anybody wanted to queue up this paper, this comes from March 2016. This is paper 12 from March 2016. We're starting on question 30. We're solving for the number of electrons that pass a point. Okay, in 1 minute, that's the time. So if we kind of go through the question, let's just label everything. R equals, and I'm going to write it like this, 5.6, instead of writing lowercase letter k, I'm going to write times 10 to the third. So that's what a kilo is, 1,000. So 5.6 kilo ohms. The potential difference V is 9 volts, and we want to solve for electrons. Passing a point in a time equal to, and instead of writing 1 minute, hopefully your instinct tells you you should convert that into the base unit of 60 seconds. So given a voltage, a resistance, and a time, we're asked to solve for the number of electrons. I'll give everybody that wants a chance to sort of have a fair chance of the calculation a head start before I say, okay, how many people kind of got stuck? How many people just need a moment? So take a second here to sort of puzzle your way through it. And see how far you can carry the calculator. Like, I know I should do this, but once I get there, I kind of forget. Okay, really try your hand at this one here. It's okay to sort of, you know, not quite see the solution yet, because by working through a number of questions like this, they become more and more familiar. And it's like, okay, here's how it goes. If you're sort of relying on, I'll figure it out on the quiz, no worries, I don't need to pay attention during class. My experience in the 13 years that I've been a teacher is that that's not going to be true. You'll be ill prepared to be successful on the exams if you're not paying attention to class. All right. If you want to know how many electrons, what we really need to deduce is the charge. Okay, and so I would always try to start with an equation that sort of includes that. So charge Q is equal to IT. I sort of begin at the end of the calculation. Like, I want the equation that's going to let me solve my final answer. And then it sort of reveals like, oh, I don't know the current. And so it's not just about what one equation do I know in physics. It's about what are all the equations that I know. If I'm given a resistance and a voltage and I need to know a current, then that's the information that I need to use to calculate the current. Okay, because I'm given a time. And so the time really is a clue like, oh, why do they tell me time? Isn't there an equation that relates kind of what I want to know and what I'm given? And even though this is measured in coulombs, not electrons, this is kind of what we need to know first, right? So we'll have to sort of convert the coulombs of charge Q into numbers of electrons. And we have to have a strategy to do that. Does anybody know the equation that relates R, V, and I? I heard somebody think I equals V over R. Good job, good job. Now you're thinking, I didn't know what I was thinking. Okay. All right, 5.6 by 10 to the third ohms. Read that. 9 divided by 5,600 equals 1.61 by 10 to the negative 3. So now we know the charge, or the current rather, in amps is 0.00161 amps times 60 seconds. And that will give us, again, the charge in coulombs. Kind of think about maybe writing a note to yourself about, I gotta know the quantities and the units that they're measuring. It's so important to know that a coulomb is an amp second. Okay, not a milliamp second. We have to know that a amp of current is a volt per ohm, not a volt per kilo ohm. Okay, we got to be able to convert kilo into ohms and so on. So I get for a charge here 0.0964. And at this point, we have to really know what are the units of that. Okay, coulombs of charge, right? A coulomb is an amp second. The base units are amps and seconds. The product of amps and seconds gives us the derived unit, the coulomb, the SI unit of charge. Not a base unit, but it is the SI unit of charge. Does anybody remember, or can anybody sort of think their way through, how do we convert coulombs into electrons? Yeah. So you have sort of the right idea in mind, and let me show you what you want to do from here on out for the rest of your academic career in studying science. Okay, chemistry, physics, the natural sciences. Write down what you're given and let the units guide your calculation. I don't want to be in coulombs, I want to be in electrons. I must cancel out coulombs by putting it in the denominator. So you said multiply, right?
I meant divide.
Okay, so you might, so if you did the calculation correctly, that's all that matters. It doesn't matter what we say. In fact, earlier I was doing a similar calculation, maybe the same one, and I think I mixed up the 1 and the 6 here, and I wrote down like 0.0061. But I just keep that number in my calculator. So like, even though I wrote it down wrong, I still got like this answer correct. And the student was like, oh, I think you wrote down, 6-1 instead of 1-6. It's like, oh yeah, this answer is right though. Like, so it didn't affect, it's like, what matters is I'm doing it right, but it's also helpful to be able to communicate if anybody else is listening, like, well, why did you say multiply? So yeah, you want to set it up like this very formally at first, where okay, in order to cancel out coulombs, I need to divide, right? Put that in the denominator. So 1.6 by 10 to the negative 19 is a number that's hopefully sort of familiar to you in your mind. If you're like, how did you know that? How am I expected to know that there's 1.6 by 10 to the negative 19 coulombs of charge in a single electron? Okay. Remember that this is a concept called elementary charge. The source of all charges in the universe are electrons and protons, basically, charged particles. And some particles are fundamental, like electrons. And so we can't divide them. If we were to scroll all the way up past all of this physics that we've learned previously this year, well, look at that galvanometer zeroed out. Sorry, we'll come back to it. Here on the data, we can find, there's our elementary charge, 1.6 by 10 to the negative 19. And again, that letter C, if you know, okay, I've measured this in coulombs, and that's where you get stuck, you need to have a way to bail yourself out of trouble. When you're like, okay, I know that it's 0.0964 coulombs. How do I get electrons? Because that's a little bit tricky, right? Like, we don't always have to carry the calculation out the numbers of electrons, but we need to know how to do it if we are asked a question like this. And so that's the way forward. It's the same computation as checking if the charge is possible. Remember that? Is this a possible charge? So we divide elementary charge into it and see if we get a whole number. We should get a whole number when we do 0.0964 divided by elementary charge. That will give us the number of electrons that pass by this point, whose current is, 0.00161 in 60 seconds, in 1 minute. So 0.0964 divided by 1.6 by 10 to the negative 19. You can kind of, think about the answer that we got up there is like, 9.6 by 10 to the negative 2, negative 2 minus negative 19, will be plus positive 19. So it should be something around to the 17th order of magnitude. And so without even, pushing buttons in my calculator, I can do sort of a rough estimate about, well, if my answers are different enough from each other, that it's really just like an order of 10 calculation, then I really don't even need my calculator here, right? I mean, maybe you'd want to sort of just prove it to yourself, like, 16, 17, they're kind of close. This is kind of close to another sort of order of 10, right? But I feel pretty good about C is the best answer here. And so if you did that calculation, you probably prove to yourself that indeed it is 6 by 10 to the 17 electrons that pass a point where the current is, 0.0061 in 1 minute. Moving right along here, so that's question 30, we said C. Okay, we'll give ourselves feedback at the end of this and sort of grade our practice quiz. Consider this just like a practice quiz. And if you give yourself feedback today and say, wow, I would only got 2 of those right out of, however many. Yeah, perfect. To the 21. So clear your calculator out. Type this in, 0.0964. Got that? Divided by, open parentheses, 1.6 times 10 to the negative 19. Close the parentheses. Now it equals. Got it? Anybody else? That's a great question, Trevor. If you are calculating along and you're not getting the same answers, I'm not getting that. You need to raise your hand and ask. Say, okay, like you maybe forgot to open parentheses. If you're dividing by something in scientific notation, you're not using parentheses, your calculator is rigidly following the order of operations, right? It's dividing by the 1.6 and then it's multiplying by 10 to the negative 19 instead of dividing by 1.6 by 10 to the negative 19. So you got to sort of give the calculator the language and understand. All right, question 31 reads, a fixed resistor of resistance 12 ohms is connected to a battery. There's a current of 0.2 amps in the resistor, and the current is now doubled. What is the new power dissipated in the resistor? My preference is to always begin at the end. You could start here and say, well, I'm just going to work my way, forward through the calculation. Eventually, I'll get at the answer I want. But I always kind of say, well, if I want to know power, I want to start with power. Power equals what? And before I even bother writing down all the equations I know for power, I want to kind of look at what I'm given, resistance and current. Does anybody know an equation that relates current and resistance to power? William? I squared R. This equation is why we send voltage or high voltage sort of power line. We send power with high voltage, not high current. This is called I squared R loss or Joule heating. Joule heating. And electrical engineers spend their careers trying to sort of solve this problem. Okay, that we lose energy due to high current that passes down a wire. Now we're asked for the new power that's dissipated, and so if there's a fixed resistor, well, that's not going to change 12. The current is 0.2, but then they double it. What's the new power? So it really is as simple as saying, well, 0.2 doubled is 0.4, so the new current is this. And we have to square it and then multiply it by the resistance 12. Once you have that in mind, that's very straightforward, right? Like that's not tough math, 0.4 squared times 12. But if you don't know the physics, you're stuck, okay? Open note quiz, you guys. Make sure you got those equations in a place not buried away in your journal where you're never gonna find them, but like open up a brand new page and go, important equations for electricity. P equals I squared R. What are the other ones? V squared over R. I times V, right? All of those equations for power. And I would even have like, well, power is energy divided by time, right? That's another way to think about power. The rate at which one form of energy is converted to another. The rate at which the EMF converts the other forms of energy into electrical energy is its power. The rate at which the potential differences convert the electrical energy to whatever form of energy they're designed to convert it into, that's power. The rate at which the sun converts its nuclear energy into light and heat that powers our world is its power. 4 by 10 to the 26 watts for our sun. That's a lot of light bulbs. So if you do that, I think you get what? C? C is the correct answer for 31. Any questions on that? Question 32 might be my favorite question of this entire problem set. And the reason why is because it's like kind of related to lab work a little bit. Look how they bold this word right here. Which measurements are taken in order to calculate the resistivity of a metal? Okay, they put that word in bold for a reason. So we'll come back to that. Resistivity. If you have an equation in mind for resistivity, it's incredibly helpful in solving this. The resistivity equation is not provided in a list of formulas. It is one that you must memorize. For tomorrow, it's one that you must have in your notes in a place where you'll readily find it. Okay. Eventually, you do have to commit these all to memory. Right? You need to start that now, because if you space that learning out between now and when you sit for the exams, you will be successful. But if you wait till like, oh, I'll just learn it the weekend before, you won't. Okay, won't happen. Probably. All right. So resistivity. Does anybody know it? RA over L. RA over L. Students that go, oh, to get resistivity, you just got to measure the resistance, the area, and the length. Those are not students that work in the laboratory. Maybe because it's 2020 and there's like, no high contact surfaces. So students that just say, oh, you need to know these three things, that's what you measure in the lab, they've never really measured anything in the lab. How do you measure area? How do you measure resistance? Because, well, I use a multimeter, I used an ohm meter to measure the resistance. Well, okay, but still, how do you measure the area? In other words, it's hard to measure the resistance of something, just like a speedometer we talked about at the beginning of the year. You can't really measure speed, right? You can measure distance, you can measure time, you can take the ratio of it. A speedometer is a clever instrument that measures distance, measures time, and takes the ratio for you. An ohm meter, a multimeter set as an ohm meter, is a clever piece of electronics that measures what? Voltage and current, and takes their ratio for you to give you the resistance. What we actually measure in the lab to get certain quantities is what this question is about. Okay, what do we measure to determine resistance? We measure voltage, we measure current. We measure voltage, PD, and current. So C and D are incorrect because we don't measure those things. Okay, what we measure is the PD and the current to calculate the resistance, just like we measure distance and time to calculate speed. Likewise, I don't know how to measure area of a circle. Other than maybe like you get a unit area, like I could cut out a square centimeter and maybe lay it down on top of a circle and like how many of them add up to the circle. I don't know, that's kind of an inefficient way of doing it. How do we usually get the area of something that's like a circle? This is a wire that we can assume is like a cylinder. It has circular cross section. And what you would actually do is you would pinch down on the wire in different places with calipers or with a micrometer screw gauge. And you're sort of averaging those different measurements because what if one part of the wire was a bit thinner than other parts? And so you get a more accurate answer by actually in the laboratory, we would measure with a micrometer screw gauge what of the wire? Its diameter. You can't measure its radius, right? That's like how you measure half of a wire. You pinch the diameter of the wire down in the micrometer screw gauge in different points. And the ruler can measure its length. We can't actually measure length. The numerator terms here, R and A, cannot be measured directly. What can be measured is the potential difference in the current, and we can calculate the resistance from that. We can measure the diameter with calipers or micrometer screw gauge. We can half that diameter and then multiply it by itself and then by pi to get the circular cross section to input here. We can measure the length with a ruler, and then we get the resistivity. So they've given you a hint. They've given you a clue by saying, hey, measurements. Not what quantities do we just plug into our equation. What measurements do we actually take? Okay, which is why B is the correct. Question 33 reads, a 12-volt battery charged for 20 minutes by connecting it to a source of EMF. The battery is supplied with 7.2 by 10 to the 4 joules of energy in this time. How much charge flows through the battery? "12-volt battery. Charge for T equals 1200 seconds on 20 minutes. We'll call this E. We'll call this B. And we're asked to solve for Q. Charge Q. Okay, measuring coulombs. A very straightforward way to approach this is to realize the definition of voltage is energy per charge. And so we can simply rewrite this as charge equals energy per volt, right? Multiply both sides by Q, divide both sides by P. And so we should be able to calculate 7.2 by 10 to the 4 joule over 12 volts to give us the charge. $7.2 by 10 to the 4 divided by 12 gives me 6,000. We did not need to know this time. We didn't need to know it. So I love calculating the time. I don't like voltage. Power is the rate at which one form of energy is converted to another. We know that there's 7.2 by 10 to the 4 joules of energy, 1,200 seconds of time. But I want to use the time in my calculation. It's a good time, 20 minutes. 72,000 divided by 1,200 is 60. And sometimes students that have an incomplete understanding of the physics, that sort of just care about the numbers, they're not really mindful that a joule per second is a watt, just see the number 60 and might choose these. If they're like, oh, I know how to calculate power, it's energy per time, 60, that's the answer. They're not really answering the question that's asked. We know the power now is 60 watts. That's how many joules per second. Every second, there's 60 joules of energy. Energizing, those charges. 60 joules per second. Power, you may recall, is current times voltage. Okay, so 60 watts of power equal whatever the current is times 12 volts, right? So we could calculate the current. So I would just be the power 60, which is still my calculator, divided by the 12 volts, which is given, gives me a current of 5, and then amps are the units for that. And so some students might calculate 5 and go, well, that's what I need here. The charge is 5 amps. No, if you're mindful of putting these letters here after your calculations, it's very clear that that's not the right answer. There's 5 amps of current. There's not 5 coulombs of charge. There's 6,000 coulombs of charge, right? We showed it with this calculation. So how do we turn this into that? All right, so now if we want to get charge, we go back to that equation that we saw for question, I think it was 30, the very first one that we did, right? Charge equals current times time. So if we take this 5 amps and we multiply it by these 1,200 seconds of time, that should also give us the 6,000 coulombs of charge that we calculated based on this equation. So both paths lead you to the same correct answer. So to speak. Two different ways to calculate. My advice to you with this worked example problem, the reason why we do these problem studies is not just to say like a bunch of practice. The drilling of it is helpful, but it's really a chance to explore all the physics, to sort of develop strategies for ourselves so that we are more successful when we're faced with sort of questions like this. And yeah, in physics class, you should be able to find that this way of thinking translates well into other academic disciplines. But, oh, this is a good way to sort of go about studying, go about thinking, to sort of attack other sort of tough problems. So taking care of the words, okay, the units, makes it, you avoid mistakes like selecting incorrectly A or B, because those numbers show up if you go about solving it this way, right? You don't want to be so satisfied with your answer here that you neglect like the physics. Oh, that's watts of power, not, coulombs of charge, okay? Sometimes it's like we get an answer that we see and we're quick to pick it without actually rereading the question or sort of thinking all the way through it. So you really do have to know what those letters mean, what are the units for measuring these things, and what quantities do they sort of represent. Moving right along here, question 34 of, we're only doing 37, up to 37 from this problem set, and then I'll sort of give you a chance to go into your journal and kind of answer any cues, kind of get your journal up to speed for a good resource in tomorrow's open note quiz, and give you a chance to sort of find some paper one questions. Who knows, you might even find the one that I'm going to assign you. You might practice those. What luck that would be. I want to try to find some potentiometer questions. Okay. 3 cells with EMFs V1, V2, and V3 have negligible internal resistance. These cells are connected to 3 resistors with resistances R1, R2, and R3 as shown. The current in the circuit is I. Which equation is correct? I'll give you a moment to sketch that circuit. Pay close attention to the lime green note up on the chalkboard there. It says, note, polarity of EMF sources for our potentiometer. Remember, we talked about that, how the positive lines up to the positive. That affects our calculation here. If you start at V1 and you follow that circuit round past R1 in the direction they're showing the current flowing, once you get to V2, note how you run into another positive terminal. That means we subtract the EMF. We talked about that the other day. We subtract the EMF when that's the case. So basically what we're sort of realizing here is that V1 must be more EMF than V2 and V3. Let's say it's 9-volt batteries, and these are each like 1-volt batteries. So 9 volts goes through. Well, then because this is wired opposite, we're going to subtract its voltage. So it's like we had 9 volts, so now we got 8. And now we got 7, you know, because let's say these are both 1. What we actually have to do is look at the polarity. That makes a difference, okay? Like that note up there in lime green. Note the polarity of the EMF source. It's important for potentiometers. It's important when we're using Kirchhoff's laws. This is Kirchhoff's second law, right? The sum of the EMFs equal the sum of the PDs. What's the PD? It's the voltage drop, and volts are equal to current times resistance. Because of Kirchhoff's first law, we know that this current I that goes into this point comes out of it, goes into this point, comes out of it. So it's the same current everywhere, which is why look at the right side of all the answers. They're the same, right? Like we kind of know that's right. The question is really about how do we add EMF sources if they're wired with opposite polarities. Again, this is the point of this question, not to answer this specific question. But for any question that's similar to it, you'd know, okay, V1 minus V2 minus V3. I have to subtract these EMFs from V1 because they're wired with the polarity that they are. Okay, so D is the correct answer here. They factor out the common I, right? Because current's the same everywhere. And remember, this is how we derive the equation for combining resistors in series. So, okay, yeah, we factor out a common I, and it's just R1 plus R2 plus R3. That's how we get the combined resistors. So it's like both of Kirchhoff's laws that you see there. Because the current is going into a point comes out of it, we can factor out the common I and realize the sum of the resistors is the circuit resistance. And it's equal to the sum of the EMFs, right? So these are the CDs, I times each of these R's. Like as the current goes through, there's a voltage drop, I times R1, I times R2, I times R3. So choice D is correct, okay? If that makes a lot of sense to you right now, you're like, that's not so bad. I can keep track. Like if it were like this were a lower little line and this were a big line, then you add them. V1 plus V2. That it's as simple as that. So maybe you have a note in your journal that's like this. Okay, negative to positive, negative. So here's just like just add EMF. Right? If it's going negative to positive, you add them. But if it's going like this, you got a positive terminal, right? And it goes around and hits another positive terminal, okay? Then you subtract. And maybe you want to make that note, more clear. Like if these symbols are confusing to your future self, you're like, well, what did I write here? Why did I draw like a fence that was kind of, So you have to know, oh, that's an EMF symbol, and I've shown that the polarity of them. Or maybe you write the notes like positive, negative, add EMF, add them when it goes negative to positive. But if it goes like this, positive to positive, right, or negative to negative, that's when we subtract. And it's not a requirement. Like I would never be the type of teacher that's like, you must take this note down in your journal. Okay, I demand it. It's really up to you. Like, how do you sort of learn for yourself so that it's like, okay, that's going to be helpful to my future self as I use my journal as a review document. Okay, like I'll be able to use that information to help me on an open note quicker. So you don't have to have these explicit notes down in your journal. I would never take away points because I said, hey, when we did question 34, you didn't write down the thing that I suggested you do. But it is a suggestion. I do think that it's helpful to have that certain notes to explicitly write to yourself, to not just let the work example sort of stand as that, like, oh, now I'll know any of them. To actually write it down so that as you're reviewing, it's like, oh yeah, I remember that. If I got another question like it, I'm doing it. 35 up there. 3 resistors, each with resistance R, connected in a network as shown. The total resistance between X and Y, way over here, is 8 ohms. What's the value of the resistor R? So we have this resistor in parallel with these two resistors, which are in series with each other, right? So along this branch, there's one path for the electrons to flow through, but along this, like once they get to this node, they can sort of go this way and this way. So the combined resistance down here is R plus R, or 2R. We add resistors in series to get their combined resistance. So we really have, kind of just think about this as like one resistor that's equal to 2R, okay, rather than just like two resistors equal to R. So we have a resistor 2R in parallel with the resistor R. The equation in general is that 1 over the resistance for a parallel circuit is equal to 1 over the sum, 1 over the resistance of the first one plus 1 over the resistance of the second one. We're summing the reciprocals of the resistance to equal the reciprocal circuit resistance. They tell us that the circuit resistance is 8 ohms. So we're given that. R1 is R, R2 is 2R. Right? So we sort of collapse down one of the branches into sort of the combined resistance and then sort of apply the correct equation. 1 over R, I could multiply by 1. I choose 2 over 2. That's the 1 that I multiply it by. You don't change the number 1 over R if you multiply it by 1, right? It's still the same number. So now I have 2 over 2R. Same thing as 1 over R. 1 over 1R, 2 over 2R, same fraction, right? So I have 2 over 2R plus 1 over 2R. Two over 2R plus 1 over 2R is 3 over, don't say 4R. Okay, remember how to add fractions. The point of doing this, the point of multiplying this by 1, and this clever one that I've chosen, is to get the common denominator so I can add them. So I have 3 over 2R is equal to 1 over 8. 1 over 8 is 3 over 2R, so 8 is 2R over 3, or 2/3 R. Multiply each side by 3/2. 2/3 of 3/2 is 1. R equals 3/2 8. 24 over 2 is 12. All right, so we did 8 times 3 is 24 divided by 2, which is 1.5 times 8. Any questions on that one? Question number 36 says, in deriving a formula for the combined resistance of 3 different resistors in series, Kirchhoff's laws are used. Which physics principle is involved in this derivation? The conservation of charge, the direction of the flow of charges from negative to positive, the potential difference across each resistor is the same, or the current varies in each resistor in proportion to the resistor value. The current varies in each resistor in proportion to the resistor value. Is kind of like Ohm's law a little bit, like, okay, each resistor has different resistances, and so the current kind of, is different through it. R equals V over I. That's not about the combined resistance, right? The first says, how does the resistor resist the flow of charge? See, the potential difference across each resistor is the same. That's just not even true for a series circuit. That's what's true for a parallel circuit, right? The voltage is the same across parallel branches. There's drops in voltage across each resistor in series, and so C is obviously incorrect. D is just like, it's a correct statement, of Ohm's law, but not applicable to this question. B, the direction of the flow of charges from negative to positive, that's something Kirchhoff, never knew in his lifetime. Kirchhoff was the first one to kind of, study, these circuits and really quantify it and realize that the energy in equals the energy out. But conventional current is from positive to negative. There was a convention that was adopted, like, okay, there's certain charges that are positive, certain that are negative, and we know that there's charge flowing around. Let's just say it's from positive to negative. That's the direction of flow of charge. And then about 40 years later, J.J. Thomson discovers the electron. And we say, oh yeah, it's really negatively charged electrons which are flowing from the negative terminal of the battery, to the positive terminal. That's actually what's going on in the circuit. So yeah, electrons do flow from negative to positive, but Kirchhoff never knew that. It really doesn't matter what direction you sort of define the flow of charges, as long as it's a complete circle. So you'll have conventional current, which is from positive to negative, which is the way that I think they showed the resistor earlier, right? Like when we did that EMF problem, we had to follow it from the positive terminal to the other one. They were showing the direction of that current, the conventional current. So if B, C, and D are all kind of, we can eliminate those, then by the process of elimination, the answer must be gotta be A. Gotta be A. Conservation of charge. Henry, do you remember the 6-time derivative of displacement?
6-time derivative?
Yeah.
I only remember the third one, which is the jerk. Like, I know it's velocity with acceleration, jerk, and then I don't remember the rest.
The fourth is the snap.
Snap. Oh.
Oh,
All right, Henry, pop quiz. Just for Henry. The battery of a car has an internal resistance of 0.1 ohms and an electromotive force of 12 volts. When the battery is connected to the starter motor, the potential difference across the battery terminals is 7 volts. What is the current supplied to the starter motor? Well, Henry works on that. We're going to discuss. Imagine, you just imagine this. Everybody put your pencils down. Henry's going to work on it. You're sitting there in your driveway. The car's not on, but you got the lights on. Okay. You put the keys in the ignition and you start the car. What happens to the light? They flicker, they get a little bit dim, right? A little bit dim. Why? We have to, yeah.
The spark plug in the car is taking
The starter is cool.
You got to draw more current, right? To like read the question. What is the current supplied to the starter motor? Okay, so we got to draw more current from the EMF source to start the car, which means what happens when we drive more current through an EMF source? Let's say you're stuck on this one. Let's say it's been a while since you've been in the AICE Physics lab and you're like, Hunter, you got an answer here? Or you just kind of okay, you got it? All right, so here's what I would suggest to everybody that's like, I don't quite know here. Does anybody know what the letter is that we use to represent internal resistance in this course? It literally is the claim you should have reached for your lab work this week. Lowercase r. There's only one equation we've ever introduced that includes that variable in it. So that's going to be the one that gets you out of trouble, right? You say, oh, I know an equation with that in it. And again, it was like when Isaiah came into class, it's like, what's the answer to the question? Say, there's an equation that helps you solve problems. There's got to be an equation that helps you solve this problem. This is physics. And you should know, hopefully, V equals E minus IR. And it is helpful, I think, to sort of go through the explanation that Michael gave us a moment ago and say, like, hey, we're drawing more current from the EMF source. Like, we can relate this to something that's maybe familiar to us. As we turn the starter motor on, we drive more current, losing more volts, subtracted away from the 12-volt car battery. So we only have 7 volts available because we've drawn so much current from the battery. Now the lights have less terminal PD available to them, right? And so they get a little bit dimmer for just a moment. We want to solve for I. We know that R is 0.1. There's a perfectly solvable algebraic sentence, which I'm sure Henry solved a moment ago. He did 5 divided by 0.1, or negative 5 divided by, negative 0.1, if you will. Yeah, combine these like terms first. So subtract 12 from both sides. The negative 5 equals negative I times 0.1 divided by 0.1. So negative I equals negative 5, or I equals 50 amps. 50 amps is what you got. Yeah, we were only doing up to 37 because we just kind of finished our circuitry stuff here. So we're not prepared to deal with a sample of an isotope that emits beta minus particles, but just since we've already started reading it. If we emitted some beta minus particles, they have a range of energies, what also must be emitted? I'm sure you know the answer to this one, Henry, do you?
This one, yeah.
Yeah, and so I always like to remember it like this. If you get a regular old electron, a beta minus particle is a regular electron, you always get an antiparticle to go along with it. So if you just get a regular old electron, you get an antineutrino, to go along with it. An antineutron, while those exist in the universe, they are not like emitted in radioactive decay reactions. So if there's a type of radiation called beta plus decay, beta plus particles, those are positrons, positron emission. When you get a positron, that itself is an antiparticle. Like that's an exotic antiparticle, a positron. And so a positron emission gets a regular old neutrino. But when we get beta minus, we do get an exotic antineutrino to go along with it. So A is the correct answer to that one. So that's like a bonus enrichment exercise beyond the scope of what your quiz is tomorrow. Let me be mindful to stop this recording here. I'll post that set of calculations for the benefit of Harrison and Ava, who decided, hey, I don't need to be here during the pop quiz. You know, guys.